Thanks for the intro, Aaron. So, like you said, I'm Nyah. I work at Altitude Networks, a security startup in San Francisco. But we don't write C++. So I wish to talk about like my experiences coming from like a C++ background into Go, and some of the mistakes I made early on, and some of the assumptions I wrongly made. And with that, I wrote like a lot of bad Go code coming from like a C way of thinking. And with that, I think a lot of developers could learn from my experiences and avoid some of these mistakes I made. So you could follow the slides. I just put the slides online, bit.ly 5 Go mistakes, so you could follow along. And there's different kind of mistakes C++ and C developers make in Go, but I picked like 3 main topics to talk about today. And the first I want to talk about is the heap and the stack, which I think a lot of C++ programmers think a lot when it comes to like memory management. And the next I'm going to talk about is memory and Goroutine leaks, which I think every Go programmer faces every day or two. And the last I'm going to talk about is like error handling in Go and how it differs from like error handling in C or in C++. And one more thing, this is a discussion, so if you have like any questions, you could meet me right after this, or during the Q&A, you could ask like any questions you might have. So let's dive right into it, like heap and stack. What is this? So pretty much in Go, a stack is a special region in memory, which is allocated to store like temporary variables bound to a certain function. And why the heap is the larger region in memory, which is used to allocate memory for the stack. And in Go, the garbage collector actually cleans up the heap, and with that, there's a lot of overhead if you use a lot of like heap allocated variables in your program. And one of the things I thought about is, how do I avoid this? How do I make my program more efficient by avoiding a lot of heap allocations? And from like a C++ background, we have the new keyword. And in C++, the new keyword allocates a variable on the heap. And I said, well, this is C++, Go, probably they stole it from C++. So if I write like my program and I avoid like a new keyword, the variable might be allocated more on the stack rather on the heap. And it wasn't really as I thought. And I think some of these biases actually affected my Go programming early on. So let me take like a simple example. So here I have a simple function called new int stack, and at the end of the function it returns a pointer to an integer. So I declare an integer using the new keyword. And what I'm trying to do here is to establish if this variable VV declared is actually located on the heap or on the stack. And coming from like C++, this makes sense for this to be allocated on the heap. So when I run this program, okay, let me switch a little bit. Let's switch here. So let me zoom. So our program is heap. The previous, let me just cap this. No, sorry. So this is the program I'm trying to run to establish if this is allocated on the memory on the stack. So if I compare this, go around minus GC flags, go. So if you look at line 12, you see the new int variable does not escape to heap, which is actually contradictory. Coming from like a C++ background, probably I assume this might be allocated on the heap, but it's not. It's on the stack of the main function. So I have another example I'm going to look at. So we have like this straightforward code, like create a variable, has a string, GopherCon 2018. When I run this, it should just print GopherCon 2018 to the screen. So when I look at this, what would you think this is allocated on the stack or on the heap? From like a C++, this is not called outside the function, so it should be straightforward stack. But weirdly, so cat heap. So looking at this, the output from the escape analysis, I see that the X variable escapes to the heap. And it's actually quite confusing. So why is that? The reason why this happens is because of the thumped printline function. So the thumped printline function takes as argument an interface. If you look at like the function specification. And what the interface does is when it takes the X variable, it converts it to an interface. And when that happens, the X is actually stored on the heap instead, rather on the stack. So we're like a C or C++ way of thinking, it doesn't make any sense. But that's actually how this works in Go. And you actually have to run some of these things to know yourself. If you make assumptions, things might get very crazy. So that's one of the first problems I encountered coming into Go. Some of the assumptions I made were not actually what I thought was happening. And one thing in Go is you should try to understand how escape analysis works. And this will help you a lot write more efficient and more performant Go programs. Given the fact that the Go language does not specify how this happens, it's mostly at runtime that you will determine whether a variable is allocated on the stack or on the heap. So, and I think it will do more escape analysis on your code. It will help you write more and more performant programs. So, as a take home for this, understand heap versus stack allocation in Go, and also try to check what the compiler output is and make informed decisions. So do not guess like I did. So that was like the first issue I faced when coming into Go. So the next thing I'm going to talk about is like memory leaks. Well, I assume like since we have a garbage collector, so I will not have any segmentation faults, like those who write a lot of C and C++ from like pointers. And in Go, the fact there's a garbage collector doesn't necessarily mean that you won't have memory leaks. And there are many causes for this. You could have like unused memory, synchronization issues with like your Goroutines and stuff like that. And some of these bugs could be hard to find. So yeah, I'd like to talk of some of the issues I faced and how you could try to solve some of these problems while you're writing your Go code. So here, the first issue I faced was using the defer statement. And with the defer statement, I have here a very simple Go program. It's idiomatic Go way of handling, like if you open a resource, like open a file, you check the error, then you defer the close. So this makes perfect sense. So when I use this in my program, things get a little bit crazy. So let's assume we have like a database monitoring tool that dumps files to a certain directory. I will regularly check that specific directory to see if there are any changes to the files, probably write some logs or do something with the files. So I have here very simple, I know it's GopherCon, so just bear with me. So this is a very simple C program. So it regularly monitors this directory for these files, and if there's an error, it prints the error to screen, or it opens and closes the file. So I just wish to demonstrate this here. So let me search for this. So this is the file. So this file opens and closes the file. It opens two files, one.txt and two.txt. So with this line of thinking, I said, okay, let me write this in Go, and let's see what happens. So here, this is my program. Let's call it logging monitor. So it ranges through this list of files, opens the files, performs like some computation, and closes the files. So this is pretty much standard Go code. So if I run this, so what I notice is we open one.txt, two.txt, one.txt, two.txt. I don't see any closing happening within the file. But it doesn't make any sense. This is like how code is done in Go. So one of the things I realized was the fact that the defer statement is not executed because the defer statement is actually bound to the function context. So until the function exits, this statement will not be executed. That's why we open all these files and they never close. And with that, you could have issues like the flush, the memory is never flushed. So your program could crash depending on how big the files could get. So what is a possible solution? What I did was I created a function literal. Since I know the defer statement is bounded to a function context, create a function literal, and I inserted my piece of code inside. So if I run this now, I hope it works. So you see, I open the file, close the file, open the file, close the file. So this just goes to prove the point that some of the things you might think work like idiomatically might not be in reality what happens within your Go program. And I did this coming from like a C++ way of thinking, like, well, open the file, and close, it should work. But here, it wasn't the case. So what did I learn from this? I learned more about the defer statement and the fact that it's tied to the function context. And unless the function exits, this statement will not be executed. And so you have like your memory flushes properly and your files close properly. And I think it's just a take home. Once you are looking at like your defer statements, you should try to take this into consideration for like those coming into like C and C++. So what do I mean by what I just said? Do not defer in an infinite loop. That's the essence. And if you do that, you have a lot of issues in your program. You could have like program crashes and things like that. So this is the second main issue I faced writing Go code. So the next issue I'm going to talk about is pointers to accessible parts of memory. So as a C++ programmer, you use a lot of pointers. And in Go, one thing I want to talk about is like the slice. These are one of the features, so like in C, like there's no slice, you just have an array. And one thing I would like you to think of when talking about slices is the length and the capacity of the slice. We know for every slice there is an array that backs the slice. And in Go, the length pretty much is the total number of elements of the slice, and the capacity is the size of the underlying array. So how does this affect my Go program? So one of the things I realized is prior to Go 1.2, there was a memory safety issue where you could actually access some of the elements in the underlying array backing a slice unintentionally. I'd probably want to do like an append function on the slice. You could mistakenly edit parts of memory you never wanted to. And this causes a lot of robustness issues with your code since these parts of memory are not garbage collected. So let's take a look at a sample program. So here I create a slice with two elements, integers, and I create a second slice, B, which copies just the first element of the first slice. And in the third element, C, I try to access the second element from the B slice. This is not supposed to be possible, but given the fact that the slice points to the underlying array, if I run this code, you'll see that in the first case, when I print the first slice A, you see the two memory addresses. In the second case, I print B, which has access just to the first element, which is Lego. But when I come to the third slice C, I somehow have access to the second element of the first slice A, which doesn't make any sense. And with this, there are so many issues you could run into within your program. You could have your logs getting off, or you have some sort of errors, you don't really know which part this is coming from. And with this was fixed later on with the 3-index slice operation, where once you're creating a copy of a slice, you specify both the length and the capacity of the slice. So with that, it prevents you from accessing these other parts, regions of memory you never intended to. And since you don't access these regions of memory, these regions are garbage collected by the GC. And with that, you have a more robust program. So let me demonstrate that. So here, take the same example, quite simple. The first slice A will create a copy. Using the 3-index slice operation, B will specify, take the first element, and the capacity of the second slice should be 1. And in the third case, C will try to access the second element of the first slice. So let's see what happens. So if I run this code, the first slice A prints correctly, B prints correctly, but in the third case, we rightly panic, which makes sense, which is what we intended to. So I think this is it's something I discovered later on while getting into Go, which I think a lot of you might find quite interesting. So I think if you're trying to copy slices in the future, you should try to take advantage of this cool feature in Go. So lessons from this. In the first case, we never set the capacity of the first slice, so we unintentionally had access to certain regions of memory. And with that, the memory is not garbage collected, and your program is less robust. So if taking advantage of the 3-index slice makes your program more robust, and no memory leaks occur, and you will not have some potential bugs. So that's it for the second, third issue. So the fourth thing I'm going to talk about is Goroutine leaks. Is there anyone here who's never had a Goroutine leak before? I don't know. All right, good. 2 guys. So with Goroutine leaks, coming into Go, concurrency is endemic in Go, but in C++, you have to use other libraries. You don't really have concurrency in C++ directly. And before I get into Goroutines, just like a background, it's pretty much a lightweight thread of execution that runs concurrently with other functions. And Goroutines communicate with each other using channels. So channel is pretty much a pipe that is used by Goroutines to share data. And with that, you could have different sorts of issues coming up with Goroutines. You could have infinite loops that cause Goroutine leaks. You could also have issues of block synchronization. Let's say channels of block mutexes are probably deadlock situations. And with that, you could have high latency within your application, and you could frequently see your program crashing. And here I would like to take a very simple Goroutine leak and talk about some of the tooling around debugging some of these issues in Go. So C++ has libraries for multi-threaded programming. And the issue I'm going to talk about here, I just have a simple function. Do something twice. It creates a single channel, creates the first Goroutine that pretty much prints done with A to the screen and returns. And another Goroutine that prints B and returns. So when I run this program, so if you notice, what happens here is only one of the Goroutines gets to be executed. You'd see done with B, and we don't see any A. In another case, we could have A executes, and we don't see any reports or any output from the B Goroutine. And this is because when any of these Goroutines writes to the channel, the function exits, and the other Goroutine is blocked. So this is a standard Goroutine leak. So how did I fix this? So what I did here was quite simple to fix this issue. I just increased the capacity for the channel to make it easier for the 2 Goroutines to write to the channel. And if I run this program now, I just increase size to 2. So if I run this, so you'll see here, done with A, done with B, done with A, done with B. So we see there's no blocking with the Goroutines running. So while investigating this, I got to tinker with some of the Go tracing tools, which I think there's an awesome tool developed by Dave Cheney on this, the Go errors package. So I generated the trace reports for the 2 programs. And with the first program, this is for the error, and the second is for the fixed. And here, if I take a look at this, let's say after like 5 seconds here, total memory consumed by the first program is like 753,000. It would take a corresponding look at the second trace for the second. So we see like 679,000. It's a little bit of gain. But if we go back, let's look at the Goroutine analysis for the two programs. Right. So let's say do something here. Do something. Which function? Okay. So one thing you will notice is for the first program, if you look at the sync block time, you see for the first program, there was a significant block timing for the Goroutines. And if you look at the second program, which I fixed, there's pretty much zero blocking. So this just goes to illustrate like a simple Goroutine leak, standard simple Goroutine leak issue might face right in Go. So let's go back to our presentation. So Goroutine leaks are very common in Go development, and there are some best practices you should follow when handling Goroutine leaks within your Go code. A very good example is taking advantage of the context package that you could use to terminate Goroutines which are no longer being tracked by the program and preventing them from running like indefinitely. The Go context package is very good for that. You could also create like a done signal or a timeout signal that actually shuts down some of these Goroutines if you're no longer using them. And you should also try to profile your code. Like the two trace profiles I just showed, I used like the package profile tool developed by Dave to generate that. You could also use the Go tool trace, Go tool profile. There's also a third-party tool, GoTorch, developed by Uber. You could use for like tracing your code. And you have the GOPS package and leak test. It is also worth noting you should check out the error group package. It actually helps a lot in tracking some of these issues in production. So you should check it out. So now I'd like to go to like the last, not really the last issue, which is error handling in Go. So in Go, we have the errors interface. So the error is a built-in type in Go, which indicates like an abnormal state in your program. And the error interface returns a string. The error function within the error interface returns a string. And coming from like a C++ background, when you write a typical program and you get an error, you either have an error string or an error code. So that's how you look at it. So let me just demonstrate what I'm talking about. So this is a simple C program where I divide by 0. So if this happens, I just return an error string to standard error, print to standard error. Then I return with an exit code. Exit failure is usually -1. And coming to like Go and this style of thinking, let's say I wrote like a simple program to like dial a URL. I don't know if this exists, but let's run and find out. So with this, Go provides the %T specifier, which can actually help you print the type of an error. So using that, I got an error from the connection from the dial, and I printed the type of the error, which is the up error type. And the advantage with this is, since errors are types in Go, you could actually explore the different kinds of error you can get within your program and actually shape the different responses you could get to these errors. So let's take an example. With the previous example, we have the connect function. And since I could determine the type of the error, I could have like different responses. Let's say I could check for the net up error, and I could also have like a default response to the errors. And if you look at the code here, I commented out formed error F, and actually showed errors.wrapf. And the reason why I did that is, if you use formed.errorf, it converts your error to a string. But if you use errors.wrapf, it actually preserves the context of your error. So let's say we have a program that calls a function, that calls a function, that calls a third function, and we wish to handle the error at the root level. If you just return a string, you will actually lose context to this error. Let's say there are different programs or different functions that return invalid connection. How do you know which function returned what error? That's where you think of wrapping your errors in Go, which is something like it took me a while to get my head around. And if you wrap your error, let's just run this code a little bit. So we see here, I wrapped the error, and I could see where the error is coming from. This error is errors with stack. So let me open the full program. Let's see errors. So with the full program here, if we take a look, I print the error, and I also check the cause of the error. So, which is actually a very cool feature with the package errors developed by Dave, which you could use in your programs. So the errors.cause function could actually help you determine what caused this specific issue. And if you have like different errors coming within your logs, you could actually know what is coming from. So this is something I wanted to highlight for like handling programs in Go, which I think a lot of you should take advantage of within your Go program. So let me close this. What? Okay. Advantages of errors. I spoke previously. Preserve the context of your error, so the passing program can handle it gracefully. And the errors, of course, could help you determine what caused the specific error you're getting in your program. And lessons learned dealing with the errors, handling errors in Go. The Go has a very, very good ecosystem for error handling, unlike C, C++. And I strongly encourage you to take advantage of this in your programs. And you should look at the errors package within Go itself and see some of the examples as to how they handle errors, so it could help you improve your own programs. So conclusively, what am I trying to share here? The first thing I'd like to talk about is understand escape analysis, how it is in Go, how the compiler makes decisions within your Go program. Don't make assumptions, because the assumptions I made were wrong in most cases. And you should actually run the program, get the compiler decisions, and actually make informed decisions rather than making guesses. The next thing I want you to think about is the defer statement. It executes only when the function returns. So if you use the defer statement within an infinite loop without bounding it to a function context, it's actually a mistake, and you get like issues within your program. Also, think about the 3 index slices and how you can integrate it in your program for memory safety and robustness within your code. One thing I would like to stress about is always try to profile your code well. C++ developers already do a lot of memory management. But for like those coming from like a non-C++ programming background, always profile your code and try to make your code as optimal as possible. And also remember, errors in Go are not just strings. They are much more. And try to wrap your errors, preserve the context, and handle your errors gracefully. So the last thing I would like to say is bringing concepts from other programming languages into Go is good, but you should know you will face some issues when it gets to certain things. And you should also be ready to challenge yourself to take out some of these concepts and actually learn to do things the Go way. And I would like to end by saying programming in Go is like being young again. So just come in with a fresh mind and learn as much as you can. Thanks very much.